Okay, now let's come to the last subtopic on this polynomial expressions. So if you see polynomial expressions, they can also be termed as functions, and I'll explain you what it is. And why this is important is the different types of partial fractions, what are the different varieties that we are going to see, that will pretty much come from one of this, and that's why this is important, okay? And let's check out the different ones, like how we saw here, different examples, the same concept, but we will be just kind of assigning some names to them. So if the polynomial just has a constant, just one term, and the one term is constant, which is as good as saying that it's multiplied by a variable raised to 0, because anything raised to 0 is 1, so it becomes a constant. So the whole expression just has one constant, for example, just 4, nothing else, okay? So that expression or function is called as a constant function, and the degree of that is 0, because that's the highest exponent of the unknown variable, 0. And if you think from this as a function, meaning that if you plot this graph, this is how it will look like. If you see a constant in an x and y axis, we have a simple constant because it just does not have any dependency. It's very independent, and there's a straight line. For example, if it's 4, then this will be the point 4, and it just cuts through that. That's what constant means. So it's very good, easy to relate this with a function, so that whenever we do these functions, it will be easier what it means. Now let's talk about a linear function or a linear expression. And all these are examples of polynomials only. So a polynomial which has only constant, then this is the first example. A polynomial expression which is called as a linear. What does it mean? The highest degree will be 1. For example, if you see 2x plus 4, which is as good as x raised to the power 1. So the highest exponent is 1, because this is x raised to the 0. So this has got 2 terms, but the highest degree is 1. So any factor or any expression which has a variable, unknown variable, unlike the first example, which is only a constant. So we have an unknown variable and we have a constant, or we could just have the unknown variable, that's also okay. And if the degree is 1, then it's called as a linear function. And this is the classic example of a linear function. If you see here, a straight line, the value of x is dependent on y. So you just draw a straight line. When you change the value of, like, it's like saying that y is equal to x. Whatever is the value of x, y will become that, something of that sort. Then the next expression is quadratic, the nature of the expression. This we are very much familiar, because we have done this in the elementary school, where let's say we have got 3 terms and it's introducing power, and the highest degree is 2, and then 1, and then 0. The last one is constant. So we have got 3 terms, the highest power is 2, and it's reducing, and with the last term as constant. If that's the case, then this expression becomes quadratic in nature. Sometimes the quadratic can be factorized, and sometimes the quadratic cannot be factorized, but this is what a typical expression of quadratic is. The highest degree is 2, and there are 3 terms, and all of the powers are descending. This power of 2, this power of 1, and this power of 0. That's what is quadratic. And quadratic typically is a parabola or something like that, which is what this function is. If you see, it cuts the x-axis at 2 different points. So the degree is 2, it cuts the x-axis at 2 different points, okay? So that's what is quadratic. And the last but not the least is cubic, where you add one more term to the quadratic, because like the way you see is each one has one extra term. The constant has just 1 term, the linear has got 2 terms, quadratic has got 3 terms, cubic has got 4 terms, and the degree or the exponents of x are in decreasing order till you get a constant. So there is a pattern to that if you see each one of them. The cubic will start with a degree of 3, and then 2, and then 1, and then 0, which is the last constant. So there are 4 terms. The first term has the exponent of 3, and hence that's the highest one, and the degree is 3, like we have seen, and this is one of the examples. And if you plot this on a graph, a cubic function will look something of this sort. And this forms the crux of one of the important chapters that you will see later, complex numbers. Complex numbers kind of was derived because people were trying to solve this cubic function, where it cuts the x-axis in 3 different points over here, right? So anyway, this is not relevant for partial fractions, but you can associate each one of this expression to the graph so that you know what we are talking about. So these are the 4 things that we'll be talking when we try to solve different types of partial fractions. We'll be using a combination of this and the concept of degree, whether the polynomial is linear or quadratic or cubic, and what is the degree of that. Based on that combination, there will be different methods that will be applied to solve partial fractions or expressing a polynomial expression into a partial fraction, and hence this was kind of important to refer.